All right, welcome back to our journey through dynamic topology. We are jumping right back in following Gordon Whyburn's incredible work, and today we're heading straight into section 13. So let's get right into it. We're going to start with a question that sounds super simple on the surface, but it really gets to the very heart of what it means for something to be connected. And just a heads up, you're going to hear the word continuum a lot today. For our purposes, just think of it as any connected space that doesn't have any gaps or holes in it. I mean, really think about that for a second. Picture a huge continent, a giant landmass that connects, I don't know, let's say New York and Los Angeles. That continent is definitely a continuum. But, most of that land, mountains, plains, entire states, is completely unnecessary for the simple job of just keeping those two cities connected. So what if we could play Sculptor? What if we could just start chipping away at all that extra stuff? Could we get rid of every single non-essential piece of land until we're left with just the bare bones, minimal connection? A kind of fundamental thread, so essential that if you took away just one more speck of dust, the whole connection would just snap? That very idea, that hunt for the essential core, is what Section 13 is all about. Okay, so this is a cool idea, but, chipping away at a continent isn't exactly a mathematical proof, right? To really answer this question, our intuition isn't going to cut it. We need the sharp, precise language of mathematics to define what this essential path we're looking for really is. And that brings us to the formal definition, the irreducible continuum. It sounds fancy, but the idea is actually super straightforward. A continuum, let's call it M, is irreducible between 2 points A and B. If it connects them, sure, but, and here's the key, no smaller piece of M can also connect them. It's the most efficient, leanest connection possible. There's absolutely zero waste. All right, so we've got a name for this thing. We have a clear target. But that leads to the biggest question of all, doesn't it? Does one of these perfect minimal connections always exist in every situation, or is it just some nice theoretical idea that might not always pan out? Well, lucky for us, mathematics gives us a really powerful and honestly very satisfying answer. And the answer is a huge, emphatic yes. It's not a maybe, it's a guarantee, thanks to what's called Whyburn's reduction theorem. This theorem promises us that inside any continuum that connects 2 points, no matter how big or messy or complicated it is, there is always an irreducible minimal connection hiding in there somewhere. And that quote right there from Whyburn himself, that's not just a nice thought. It's a rock-solid guarantee. It's a foundational theorem in topology that basically gives us permission to go looking for these essential skeletal structures inside any connected space. It's the green light for this entire line of thinking. So, how in the world can we be so sure? How can we prove this is true for any continuum? Well, the logic behind the proof is it's incredibly elegant. It's less about building something new and more about making a perfect argument. Let's walk through the big idea. The proof is basically a brilliant process of elimination. First, in step 1, you imagine gathering up every single possible subcontinuum within our bigger space M that successfully connects our points A and B. Then, for step 2, you organize this giant collection by a simple rule, inclusion. You just order them from biggest to smallest. And then, for the final step, we bring in a bit of mathematical magic to seal the deal. And that magic is called Zorn's lemma. Now, don't let the name scare you. The core idea is actually something you can totally wrap your head around. Think about those Russian nesting dolls. Zorn's lemma is basically the mathematical rule that says you can't just keep opening smaller and smaller dolls forever. At some point, you have to hit the last smallest doll that can't be opened. That's your minimal element. In our proof, Zorn's lemma guarantees that our process of finding smaller and smaller connecting pieces has to stop. And where it stops, that's our irreducible continuum. Okay, so we've proven they exist. Awesome. But what are these things actually like? What makes them so special? How are they different from the bigger, clunkier continua that they live inside of? Well, where they really show their true colors is when you try to break them. We're going to use the idea of cut points. These are basically points that, if you remove them, you would split the space into different pieces. Let's see how our new minimal structures handle this kind of stress test. And this comparison just lays it all out perfectly. On the left, you've got your regular, everyday continuum. Think of it like a thick, sturdy rope. It's robust because it has redundancies. You can snip a few strands here and there, and the rope still holds. But on the right, the irreducible continuum, that's not a rope. That's a single, taut, perfect thread.
The connection from A to B is so fragile and essential that every single point along that path, except for the endpoints A and B themselves, is absolutely critical. You remove just one, and the entire connection is severed.
So, where does this leave us? The really crucial point here is that the reduction theorem isn't just about answering one little puzzle. It actually hands us a brand new, powerful tool for analyzing spaces. It's like being able to strip away all the noise and see the hidden skeleton underneath any connected object. This gives us a much sharper lens to see the deep underlying structure of things, which paves the way for everything we're going to explore next.